Welcome to our video on using the material testing machine for mechanics and materials. We're going to use a PASCO ME-8236 machine to be able to characterize some of the mechanical properties or material properties we've been discussing in class. This is the machine. If I turn to the right, it raises this head upward. If I turn to the left or counterclockwise, it lowers it again. You will find a couple of fixtures in the kit, and the larger ones are the ones we're going to use initially for some of the thicker samples. When we say thick, they're not that thick, maybe a millimeter or so, but these are great for being able to clamp down on the material that we have to test. So, or at least the metals that we have to test. So we're going to put one in the bottom, as you see here. So you just twist, okay? And you don't need to go make it tight. You want it to still be able to rotate, like you see there. When I put this other one, I actually what you should see is actually they should be sitting out when you get them kind of like this with this threaded rod on both ends sitting there, and so you're going to put this other piece up in the top, turn it like this, and again, you don't want to tighten it all the way. It should be able to rotate. Now, we're going to get a sample, or you will be provided with one at least, and here is a nice example. This is a piece of aluminum, okay, that you see here. And before we put it in the machine, what we want to do is we want to use calipers. And so with calipers, make sure that you return them to either their case or to a nice soft location so that we take care of them appropriately. The wooden table is really not that bad for them relative to like putting on something hard. But anyway, so what you're going to do is take this caliper and you're going to measure the cross-sectional area or the cross-sectional dimension. So that's probably around 6 or so millimeters in that dimension. And this one is about, well, so this is about 0.8 in the thickness dimension. Okay. So we have these measurements, record them. And then also take a look and go ahead and measure the approximate testing length or the gauge length. And how do you do that? This doesn't have to be super precise, but you want to pretty much get an idea of what the length of the test region is. And that's kind of where it just becomes thin on either side. So this one's about 58 millimeters. Length. Next, what we're going to do is install a sample. So we go ahead and we bring it over here. We might have to pull this out a little bit. When I pull this, it's like this front piece that's been very nicely designed by the staff here at Rutgers to fit in this machine. And then we're going to go ahead tighten just with our fingers so we get it kind of centered, kind of stable there on the bottom. And then we'll come up over here and we're going to tighten over here as well. Okay, just like that. Then we get our wrench, Allen wrench, and we come over here. Want to get these pretty tight. So, okay, stop turning. Stop turning. Okay. Stop turning. Okay. Okay, wonderful. So don't be too concerned about not putting a little bit of strength in there. Sometimes these things are tricky to get right, but after you do one or two, you'll get a feel for what it should be. I guess then the experiment will be over. Now, staff have also designed these nice coverings to protect us. Now, we don't really expect there to be shards of material flying around, but that will provide an extra barrier between us and the sample. Now, let's go ahead and get to the software. You'll see that there's this folder, Fall 2023 Tensile Testing Data, or maybe in a future semester if we use it, another name. And what you want to do is go ahead and create a folder for your team. So we'll call it Team Fun 230923, that's the date. And we will also make a copy of this. So we're gonna just do a Control-C, yes, and then a Control-V in here. And we're gonna rename it to just be our Team Fun 230923. Okay, for this lab, all the data we collect can go into this PASCO capstone file. And why are we doing this? Well, we're doing it so that we have a place where our data remain safe or somewhat safe and collected. And we also have an opportunity to go ahead and make sure that we don't damage this template file for future users. Okay, when we double click on our Team Fun 230923.cap file, the following appears. Now there are no data here. It's a nice blank experiment for us to use. When we are ready, we can hit record. And what's going to happen here when we hit record? Well, the machine is going to be talking to the computer, and it's going to be collecting the data from the force or load cell that you have on the bottom, and we'll also be collecting data on the change in position of this top head as we turn the crank. Typically, we want to be turning such that the speed, you probably can't see it because it's so small, but it's less than 20 millimeters per minute, and it's more or less steady when we get ready to do a test of the elastic and plastic properties to break with a material. Initially though, we haven't necessarily tightened or put the sample under sufficient tension such that it's starting at the beginning of the stress strain curve. So what we are going to do is we're going to hit record, which will allow us to start seeing data, and we'll start turning clockwise, which will allow us to kind of get things kind of going a little bit. And this, I'm not doing the 10 millimeters per minute. I'm just trying to put in a few newtons of force, and then I'm going to come back down. Okay, and I can go back up, and I can see what the values are on the left, in fact, right here. And we'll just leave it a few newtons, and then we'll hit stop. So this is more or less going to zero our data collection so that when we start the next run, or the next recording run, it will zero that out, and that's kind of where we can start the beginning of our stress strain curve. Now, if you have multiple runs, okay, so you can go ahead and delete them. You can also Control-Z. I've done it before where I've accidentally deleted when I didn't want to run or didn't want to delete. But those runs are there. You can also go back, and I'll show you in a little bit. You can play them back. So what we're going to do now is we're going to record a collection of data for a stress strain curve. In this case, it's just position. I'm going kind of nice and slow, but trying to keep it even and consistent. Keeping it even. Okay, the sample is plastically deforming, and I'm trying to keep it nice and easy. Nice and easy. It's still going, still going, still going, still going, still going, still going. All right, keep churning like so. And we're going to go all the way until it finally fractures. Might take a few seconds here. And keep going. You see this, and that's it. All right. And then we can go ahead and we can hit stop. Now we've collected our run. And even though this is force versus position, not stress versus strain, we can see the behavior as being elastic. And we're going to try to figure out what the slope is, to figure out what the elastic modulus is when we plot stress versus strain. And then this is the plastic region. Okay, and you could say, oh, maybe the ultimate tensile strength is somewhere around here. The yield strength is probably somewhere around here. And then we have fracture occurring over here. Okay, and what you see in the sample itself, it's quite nice here. This broke nicely. Let's see if I can kind of zoom in there, but you can see that it fractured, and there's maybe a little bit of necking there. Okay, but what's important is that it didn't break near the grips; it broke toward the middle. So what do we do next? Well, we can take this apart, and that you'll do to load it again. But what I want to show you at this point is how to go about getting the data and processing it for the lab. So here we're going to go to File, and we're going to go to Export Data. Okay, and you have the option to select the runs that you want to export at any given, after any given run. If we only want one run, which really we only need the second one, we can deselect all, and then we can take the time for run number 2. We can take the position for run number 2. We can take the force from run number 2, and for fun, we can also take the speed. Okay, so we have the data that we want. If you want, it's okay. If you want to collect the data and export all the runs in one shot, that's fine too. We'll show you how you can parse through the data effectively in just a minute. So we're going to export to File. This is Team Fun. So we'll call this CSV file, and we are exporting to CSV format, comma separated values. We'll call this aluminum, and this was our 230923. 1, we'll call it, all right, because it's the first test that you might do. Or maybe it's better to call it run number 2, okay? Maybe I'll go back and I'll change its name, actually, just so that it's, we'll call it, this is run number 2. You know, either way, you probably want to have a notebook and keep track of what's going on. And when you open up the CSV file, actually, it will be pretty obvious that it's run 2. So how do you process this? Well, you could use Excel or another spreadsheet program. What we've done for the course is attempted to make it a little bit easier by creating a Colab-IPython script to help us process these data. So here, I guess I went quickly, but if you go to the bottom, okay, this is the mechanics and materials page on engineering-content.com, and we come down here, and there's a Colab file that we can open up. And if you go about attempting to run this, it's going to say you need to log into your Google account. So go ahead and do that. I'll do that quickly. And what do we see? We see the same exact thing. And if you like to keep things straight, you can go ahead and you can save a copy in your drive, right? Since this, you might want to keep this as the first aluminum sample tested. So we've used some Colab in the course already. You run the first cell, you get the warning, you're going to go ahead and run it. Now what's maybe a little bit different here is that this is going to keep spinning. We want to go ahead while it's spinning, click on this new icon for browse, and we want to go to our team fun directory and find our CSV file. Okay, so we select that, and now it brings it in. Okay, now for the name in the next cell, we're going to copy this right one. Now this happens to be the same, but if you attempt to load multiple instances of the same file, it will change the name slightly. So make sure you use this one on the right, paste it in, go ahead and run that as well. And now it gives us a preview of the data. We see that there's the time, there's the position, and there's the force. And we have speed as well. This one right here will go ahead and plot the data for us. Now, it's a little bit confusing what we have here. And you know, there are no options, but Python or Matplotlib does a nice job of actually this might just be Python. We will use Matplotlib, but anyway, the plotting, what we see here is that these are the indices, okay? So in other words, on this left side, there are 3,186 rows. We were taking data at 50 hertz, so 50 samples per second. And this index, or these indices, are going to be important in a minute, you'll see, because we want to select the appropriate data. The colors designate the time, okay, which is, it ends up, you know, since it's using this scale, this axis, it's much less than the force that we were putting into the sample. Position is also much less, and speed is also much less, okay? But we're going to be looking here to see, okay, where did the data start, where did it end? And these indices are essentially, you know, marks in time. So if I waited a long time to start the experiment after hitting record, then I would expect to see that the start would be, you know, further along down here, maybe it'd be 1,500 samples instead. So where did this start? Well, this is where you play around a little bit, okay? So we're gonna say, let's try 350, okay? And I haven't processed these data before. This is, there's been no break since I've collected the data. And let's say that we don't care so much about this point for now. Let's say we end maybe somewhere around, I don't know, 2,700. We'll just try it out. And we can change these numbers, okay? So that's the start index, 350, the end index, 2,700. And we'll go ahead and run. And what's this going to do? It's going to give us an error, because what we need to do is we need to change the name of the column that we're pulling in to the appropriate name. So we don't have a run number 1 here, it's run number 2. So be careful there, all right? And wow, okay, that's pretty nice, right? We see kind of the force and the and how it's changing over position. Let's see. I think we want to push it a little bit. I think we want to get a little bit more data. So let's jump out. Let's put 2,800 here. Go a little bit further, and let's maybe start a little sooner. 250. Let's see what happens when we do that. So it'll plot for us. I hit Control Enter instead of the play button. Okay. Okay. So maybe that's it's hard to see, but it's a little bit slope. So I'm gonna up this number a little bit to 300. And I think this is capturing it pretty well. I'll go a little bit past here, but I think I'm going to end up going back. And I don't think we're going to, yeah, so that's kind of nice. It's curving down. It's starting to break. And this is pretty good. This is starting pretty close to the beginning of the curve. So I'm pretty satisfied that we've got the whole thing now. Now we want to plot stress and strain. Well, to do that, right, we need the force and we need the area. So in this case, my sample was maybe about 6 millimeters wide, and it was actually about, we'll change this. It was actually about 0.8 millimeters. So I'm going to do 0.8 divided by 1,000. Okay, so this is millimeters times millimeters, and that's going to, or this is now in meters. Okay, both of these are in meters, so I'm going to get units of meters squared. The initial length, I'm going to reduce. I think it was probably closer to 60. Okay, but you measure your sample and you'll see. Okay, from here, we have code that allows us to calculate things like the modulus of toughness, an estimate for the ultimate tensile strength, and a nice plot. Okay, so let's see what it looks like. We're going to hit the play button, and here we go. So the modulus of toughness has been integrated or evaluated through the trapezoidal method, okay, with the data. All right, so the area under the entire curve is something like 45,000 kPa or 45 megapascals. And the ultimate tensile strength is quite high, 559 in this case. Right? So that's for the overall sample. Now, let's go ahead and let's take a look at just the elastic region. Okay, so this. So I'm going to use the same starting index that we used up here, so 300, but I'm going to use a different end index because I just want the elastic region. So let's come back here and we say, let's try like, I don't know, maybe let's try 700, okay? So that's like somewhere in between 500 and 1,000. And we come over here, so we're gonna lower this down to 300, and we said we'll go to, what did we say, 700? Yeah, we said we go to about 700. And we plot, and you can plot this multiple times quickly. All right, what do we have here? So we have the measurement of the slope. Okay, so there's a little bit of curve here and a little bit of a curve here. So for the sake of calculating this elastic modulus, it's doing a fit. You know, it may not necessarily be the best because this is kind of sloping this way, this is sloping this way. Maybe for the sake of plotting the elastic modulus, I'll actually narrow the range a little bit. Okay, we have an estimated yield strength of 371 megapascals. Okay, that's possible, and then we have modulus of resilience calculated here. Now, as I narrow that range, I expect that the yield strength will go down a little bit because I'll be further down here. And I also expect the modulus of resilience to go down, okay? This is not exact, all right? But it gives us a rough idea, all right? So we'll go, let's change, let's do like 350. And let's do 650, okay? All right. So now, yeah, that seems to be starting off nice, a little bit less here, okay, tapered. This line seems to fit pretty well to this blue data line that we have here. And if we looked at the elastic modulus, it's coming in at 61, okay, gigapascals. That's maybe a little bit lower than we'd expect for aluminum, right? Aluminum we expect to be 70 gigapascals. But there could be errors in the measurement, either in our dimensions that we've measured, or even some compliance in the machine, or errors in the measurements of force. error in the length, okay, or extra compliance in the setup. Okay, all these things that could happen with an experiment. Nonetheless, this elastic modulus is such that it's plausible for aluminum. And so the last thing to show here is that if I want to upload or paste these graphs or share them with other people, all I have to do is right click and do save image as, and I'm gonna go to my folder, my Team Fun folder, all right, and we'll just say, okay, this is the aluminum sample, right, that we had. Oops, I don't want to save it as CSV. It's going to save it in a different format, and we could say stress strain overall for this one, okay, and this one we can right click and we could say this is going to be elastic, okay, and if we close this or minimize everything, or we come over here, we can go to Team Fun. We can pull up, I don't know, I'm sure just once here, these plots, okay, and it's not bad quality. The default is not bad quality. I have it here, so we could have changed the sample number. It's okay, if you want to do sample number 1, but this is the resulting plot that we are able to get, or one of the resulting plots we're able to get from our tensile testing experiment. Thank you.